Hey guys, I'm Bad with Math, and today I'm going to be showing you how to solve optimization problems in your calculus class. So optimization can be a very difficult concept to learn, especially when you're learning it for the first time in AP Calculus, AB or BC, and you don't really understand where to begin. That's the main issue that the students have when they're learning it. So we're going to go over a few problems today and understand how we're going to optimize these problems. Now, to optimize means to maximize or minimize some sort of value. So you're going to know that it's an optimization problem in the question. For instance, here it says the area of a rectangle is 64 square feet. What dimensions of the rectangle would give you the smallest, right here, smallest perimeter? Smallest means that we're trying to achieve some sort of minimum. And that means that we're going to be optimizing. And of course, with anything in calculus, we're also going to be deriving. So we're given a rectangle. So we have a rectangle. I'm just going to draw it out really quick. It doesn't hurt to draw it out. And the rectangle has an area of 64 square feet. So I'll just write it there. What dimensions of the rectangle would give you the smallest perimeter? So we have two different formulas we can write. And with optimization problems, we're going to be using some sort of system of equations typically. So I'm going to set up my system. When the area of a rectangle, the formula for the area of a rectangle is just length times width. And then the perimeter of a rectangle is 2L plus 2W, right? You just add up the four sides. These two are the same and these two are the same. I'll assign L and W for the rectangle. So now we want to first understand that our area is actually 64. So we can replace this A with 64. And from here, we're going to use this perimeter equation in order to solve for one of these two variables. Because if we know that L is, let's say, 4, we know that W has to be 16 because 4 times 16 is equal to 64. So we're going to try to find one variable first using optimization practices. So what I'm going to do is I'm going to convert this into W equals 64 over L. And what I did was I just divided by L on both sides. So now we have an expression in terms of W. And what I can do here is I can replace that in the bottom equation. So P equals 12 plus 2W. P is going to equal to 2L plus 2 times 64 over L. And then I'm just going to simplify. So we're going to have 128 over L. And now what I'm going to do is I'm going to take the derivative of the perimeter with respect to the length. Right? And we're just going to end up with 2 plus 128 over L squared. That's going to be minus. This is because if you take derivative of 128 over L, you end up with, really this is the same thing as 128 times L to the negative 1. You do the power rule and you end up with this value, which translates here. So now what I'm going to do with this equation, we're trying to minimize, right? And how do we know if there's a maximum or minimum? We set the derivative equal to 0. So that's why I found the derivative in the first place, and we're going to set it equal to 0. And all I'm going to do is solve for my critical numbers. I'm going to move this to the other side, so we're going to have 128 over L squared, and then we can multiply by L squared on both sides, and we'll be left with L squared equals 64, or L equals 8. I didn't write plus or minus 8 here because we're trying to find a length, and you can't have negative length. That doesn't make sense. So we'll be left with a positive 8 there for our L. And then very simply, we can just plug in 8 into L to one of our, well, realistically just this one. So 64 equals L times W. If we just plug in 8, that means our W is going to be 8 as well. So our final answer would be 8 by 8 feet. And that would be our dimensions for this basic optimization problem. So here we have a much harder example compared to the previous one. And we'll notice first that we have a rectangle is bounded by the x-axis and the graph of a semicircle defined by y equals the square root of 25 minus x squared. In case you don't know, which it's very common that you don't know this when taking calculus, but if you have the formula for a circle, which is centered around the origin, so 0, 0, this is the formula for a circle, and we just solve for y, we'll end up with r squared minus x squared. And basically what this means is, plus or minus. What this means is, this is the way to write a circle in function form. However, because we have plus or minus, we're going to have, again, a circle is not a function, right? It has multiple x points at the same y point. So when we do the plus or minus, we see that we have plus. What it does is it only takes this top half of the circle, which is what makes it a semicircle. And that's just something to know. If you're ever given this and not the graph, you'll most likely be given the graph, but just in case, so you know how to understand what a semicircle looks like. Which means that on this graph here, we're going to have the semicircle going like this from -5 to 5. And it's a rectangle bounded by that semicircle and this x-axis here. So it's going to be a rectangle going up and like that. And if we continue reading the question, we have what dimensions should the rectangle have so that its area is at a maximum, which this tells us that we're going to be optimizing. Now let's set up our system for we're going to find area, right? Or we're not going to find area, but we're going to use the area formula. And area is known as base times height, right? So we have our base and our height. But notice that our base goes from here to here, which is x, but also from here to here, which is x as well. So for our base, I'm going to write it as 2x, because when we do the math, we're not going to account for the negative x's, and so we have to sort of multiply our positive x by 2 in order to figure out the actual base of the rectangle. So I'm going to write 2x, and then for our y, well, since it's bounded by the x-axis, we'll just keep it going from 0 to whatever y value, and that means we're only going to be working with 1y. So we don't have to multiply that by 2 as well. And then it asks for the area, and we're given that y equals the square root of 25 minus x squared. Well, this is really simple because we can just substitute y into here. So we're going to have that the area of this semicircle is equal to 2x times the square root of 25 minus x squared, which I'll rewrite as a fractional exponent. And then when we take the derivative, we're going to be using the product rule and the chain rule. So let's take the derivative with respect to x. The derivative of 2x is just 2, and we keep the other one the same. 25 minus x squared, so the 1/2, plus 2x times, bring down the 1/2, and then keep the inside the same. And then we're going to have, take the derivative of the inside, negative 2x. When we simplify this and put it back into rational form, we're going to have 2 times the square root of 25 minus x squared minus, these two cancel, we have the minus from here, and these x's make x squared, 2x squared over 25 minus x squared in the square root. Now I want this all over the same common denominator, so I'm going to multiply this part. So I'm going to do this here really quick. 2, here I'll do it in red. 2 times the square root of 25 minus x squared over or times the square root of 25 minus x squared over the square root of 25 minus x squared. Because we want the common denominator, and this just has a denominator of 1, and this has the denominator of square root of 25 minus negative x squared, or just minus x squared. So on the bottom we'll have that denominator, which is great. And on the top we're going to have 2 times these two square roots, they'd cancel the square root out. We're just left with 25 minus x squared, which is 50 minus 2x squared. And then we're going to add it with the numerator on the other side. So this would be 50 minus 2x squared minus 2x squared, which is just 50 minus 4x squared. So this is 50 minus 4x squared over the square root of 25 minus x squared. And because we're optimizing, trying to find a maximum or minimum, we're going to set this derivative equal to 0. I'm going to try to find the critical points. So we set 50 minus 4x squared equal to 0, and we end up with 5 over the square root of 2. We do end up with plus or minus, but remember that we're just going to take the plus, because anyway we're going to account for the negative section of the x. And then find when the bottom is equal to 0, and we'll just get x equals 5. And what we're going to do now is test if there's a maximum or minimum. I know we didn't do it on the last one because we only found one critical number, but we should always verify. In this case we have to verify because we have two critical numbers. So we're going to go from 0 to 5 root 2 over root 2, and then to 5. If we plug in a value like 1, we get 50 minus 4, which is positive, and then the bottom is always going to be positive until after 5. After 5, the value will be imaginary. So this is positive. And already knowing that the value after 5, because if you plug in like 6 here, you get 25 minus 36, that's negative, and anything inside the square root that's negative is imaginary. So we can just put like an I here, and we know that from finding a maximum or minimum through a numerical analysis, we will not get any maximum or minimum here. So this is not our critical number. But just to double check, I'll plug in a number like 4. If we plug in 4, we get 50 minus 64, which is negative. And then on the bottom, 25 minus 16, that's the square root of 9, so 3, that's positive. So we'll have negative over positive, which is just negative, meaning that here we have a maximum. And so this is the x value we're going to be using. So we know our x value already, but we need to find our y value. And what we'll do is we'll just plug in our x value into the equation for y. So down here, y equals the square root of 25 minus 5 over the square root of 2 squared. This becomes 25 over 2, and this is 25. 25 or 50 over 2 minus 25 over 2 is just 25 over 2. So we have 25 over 2, which means this is also the square root of 5 over 2. 5 over the square root of 2. And then we have to find the dimensions of the rectangle. So very important when writing this down. We know that the y value is 5 over the square root of 2. So we can say 5 over the square root of 2 by, and now you're thinking to put 5 over the square root of 2 for x. Do not make this mistake. Even though x is 5 over the square root of 2, the base of our rectangle is 2x. So we have to multiply this by 2 to get 10 over the square root. And then these are our dimensions for our rectangle. So here we have a much larger problem in terms of reading, but you're going to see this problem is actually quite simple to do. A cryptography expert is deciphering a code. To do this, the expert needs to minimize, so we're optimizing, the product of a positive rational number and a negative rational number. The positive number is exactly 8 greater than the negative number. What's the final product? So first, I'm going to label this positive rational number as x and this negative rational number as negative y, so that the y is actually positive. Or, I'll keep y positive, so xy. And then the positive number is exactly 8 greater than the negative number. So let's make our system. We know that there's going to be a product of x and y. It's actually the product we're trying to find, and it has to be minimized. And then the positive number, so x, is exactly 8 greater than the negative number. So we're going to take x is equal to y plus 8, because it's 8 more than the negative number. So this is honestly a very simple problem. What we can do is we can substitute x here. So instead of x, we can say y plus 8. So p equals y plus 8 times y, which is just p equals y squared plus 8y. And then we just take the derivative in respect to y, which means that y squared becomes 2y and this becomes 8. And then we need to set this equal to 0, which means that we'll get y equals negative 4. Well, that's pretty good. And then we know that x, well, let's first check to make sure there's no disparity. So, this is really simple. We plug in like negative 5, we get negative 10 plus 8, negative. Plug in 0, we get positive 8. So yeah, this is a minimum. And then from here, we can just plug in y equals 4 to the second equation. So we're going to have that x equals 4. And then the product of these two numbers is just negative 16. So even though this one may have looked a bit more difficult because of all the reading and because the wording doesn't have using a specific formula, you just have to kind of really start thinking deeply at the beginning portion of what are we trying to find and what is given to us. In an optimization problem, you'll notice we always have some sort of formula and some sort of constraint. So this is our constraint, this is our formula. Now we're on to our next problem, and I'm showing a lot of problems for this because this is a topic that many students struggle to understand. I remember when I first started, I went through like probably 20 or so-ish problems, and I had the answer with me and the steps showing, and I still didn't know how to solve it until like one point I guess it just clicked for me. But starting is always the hardest point. So let's go through this problem. Find the point on the graph of f of x equals the square root of negative x plus 8 so that the point 2, 0 is closest to the graph. This is going to look something like this because it's reflected across the y-axis. And we want the point 2, 0 to be closest to some point on the graph, some point x, y. Okay, so obviously we know that we're dealing with optimization because it says closest, that's minimum. This is our constraint, so I'm going to write y equals negative x plus 8. And now we need our formula. Our formula here is actually in the word closest. Closest signifies minimum distance. So what we're going to be using is the distance formula, which is the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, let's plug this in. Our x2 will be our x, and then our x1 will be our 2. So we have x minus 2 squared plus y2 is just y minus y1, which is 0. I'm not going to write minus 0, so I'm just going to write y squared. And then I'll remove this. So you also have to know some formulas, right? It could ask about circular formulas, right, involving a cylinder or a cone even. But I doubt that they'll give that on the AP exam. From here, we're going to plug in our constraint into our formula. So d equals x minus 2 squared plus, this is y squared and this is y. When we square y and we square this side of y, the square root goes away and we just have negative x plus 8. So that's actually what I'm going to write, negative x plus 8. And then I'm gonna expand this and add it with this. So we're gonna end up with x squared minus 5x plus 12. And then I'm actually gonna write this in fractional form. So like fractional exponent. And then from here we just take the derivative, right? So the derivative of the distance in respect to x is equal to 1/2 times x squared minus 5x plus 12 raised to the negative 1/2 power times 2x minus 5, which is the derivative of the inside. And we can rewrite this as a radical form. So 2x minus 5 over 2 times x squared minus 5x plus 12, which is equal to 0. From here, we are going to find the critical numbers, so not just equal to 0, but also undefined. Unfortunately, or I guess fortunately, if you try to find the critical numbers when they're undefined, your x will be some complex number, which means that there's no real value for x, so we don't have to worry about the bottom. On the top, we just make it equal to 0. We find that x equals 5 over 2. And we're going to do our numerical analysis just to make sure. On the bottom, we're always going to have positive, so it just matters what's on the top. If we plug in 0, we end up with 0 minus 5, which is negative. If we plug in 6, we get 2 times 6 is 12 minus 5. So this side is positive, which means we have a minimum, which is what we're trying to find. And it's also our x coordinates for our point. Now we need to find our y coordinate, which we can do by plugging that back into y. We end up with the square root of negative 5 over 2 plus 8. We can rewrite 8 as 16 over 2, and then 16 minus 5 is 11. So our y value is the square root of 11 over 2, meaning that our final answer would be the point 5 over 2, comma, 11 over 2 in the square root. Alright, for our last question, I'm actually going to have you do this one by yourself, and I'm going to show you my end result and see if you guys got the same answer or not. Maybe you can compare. So we have a Norman window is constructed by adjoining a semicircle to the top of an ordinary rectangular window. Find the maximum area of the Norman window if the total perimeter is 16 feet. So really quick, I know earlier in the video I showed you semicircle, like the formula for it in terms of like a function. Here, since we're talking about area and we're not on an xy plane, we can just use the area of a circle and divide it by 2 in order to use the semicircle. And just for reference, the window would look something like this. So we have a square here, a square here, and then the semicircle on top. Okay? Oh, and this is a calculator question, and be sure to write your answers to the 4 decimal places. Alright, pause here and good luck. So, in the end, I ended up with 17.9231 feet squared. I accidentally made the mistake of putting pi plus 1 here, and it took me a lot longer. But yeah, I just found the equations for the optimization. Notice that they're very long. They cut off at about here. This is me converting it now. And then I used this here, this, and I derived this to get this derivative here. I wanted to group the pi plus 2 just to make it easier. And this was the x value that I got. So hopefully you got it right, and I hope you're able to learn from this video. Thank you for watching.